Welcome to Lecture 24, in which I want to discuss the behavior of gases, because these behaviors are going to provide us with pretty deep insights into some fundamental laws of thermodynamics that we'll be dealing with in upcoming lectures. And in particular, I want to deal with something called the ideal gas. Now, when you hear the word ideal, as for example, you talk about, say, an ideal battery or an ideal frictionless situation, you pretty much know the physicist is talking about something that doesn't really exist. Well, in the case of ideal gases, that's not quite so. Most common ordinary gases, like the air around me right now, are in fact very, very close to behaving like ideal gases. So ideal gases are not some vague idealization and theoretical thing. They're a very, very good approximation to many, many real gases. But we're going to look at ideal gases because they're going to give us tremendous amounts of insights into this contrast between the macroscopic picture presented by thermodynamics, in which we have temperature and pressure and heat flows, and the microscopic picture of matter, in which we understand the behavior of matter as following from the application of things like the laws of mechanics to the individual particles that make up matter. An ideal gas is particularly simple, and it's easy to understand, and it's easy to characterize, and that's the reason we want to look at ideal gases. Other materials, solids and liquids, are much more difficult and complicated to understand, as are gases that exhibit non-ideal behavior. The ideal gas is simple primarily because its molecules are far apart. They exhibit very few interactions. The only thing they really do in a really ideal gas is they undergo collisions occasionally, and in fact, you can even idealize to the point where they don't do that. The behavior of ideal gases, because of that, becomes basically universal, independent of the gas. It doesn't matter whether I've got helium or hydrogen or oxygen or nitrogen or air or neon. Well, it does matter a little bit in ways I'll get to at the end of the lecture. But the main behavior of ideal gases doesn't depend on the nature of the gas. The constant volume gas thermometer that we talked about, for example, you can put pretty much any gas in it. Although if you really want to get down to low temperatures, you want to put in something like helium that has a very, very low liquefying point. But the point is, in the realm where the ideal gas approximation applies, gases behave like this regardless of the nature of their molecules, regardless of what kind of gas they are. So let me begin by looking at some empirical, that is, experimentally determined behaviors of ideal gases, and then we're going to switch to a theoretical analysis that's going to explain these behaviors. So here are some experimental results that people knew about long before they understood what I'm going to be getting into in this lecture, the molecular picture of what's going on with gases. Experiments with gases showed that if you fixed the temperature of a gas, then the pressure of the gas would be inversely proportional to its volume. So at a fixed temperature, if you compressed a gas, its pressure would double if you, for example, dropped its volume in half. Its pressure would half if you doubled its volume. The product, PV, would remain constant at a fixed temperature. So that's the inverse relationship. Pressure times volume is a constant. If pressure goes up, volume goes down. If pressure goes down, volume goes up proportionately. It's an inverse relationship. All these individual descriptions about individual behaviors of gases have particular names named after the people who discovered them, but I'm going to cut to the chase and go right to the universal law that talks about ideal gases. If you change the temperature, the quantity P times V, pressure times volume, changes proportionately. If you've got a gas with some value of P and V at some temperature, say 200 kelvins, and you double the temperature to 400 kelvins, P times V will go up. P may change, V may change, but the product PV will double if you change the temperature or double the temperature. And notice when I talk about doubling temperature, I don't mean going from 10 degrees Celsius to 20 degrees Celsius. That's not a doubling of temperature. A doubling of temperature is on the absolute scale where the zero is the true absolute zero. So I mean going from 200 kelvins to 400 kelvins, from room temperature 300 kelvins to 600 kelvins. That's what I mean by a doubling of temperature. So I'm talking about absolute temperatures here. You change the amount of gas, how many molecules there are, PV also changes proportionately. Double the amount of gas, and either the volume will double and the pressure will stay the same, or the pressure will double and the volume will stay the same, or some combination of those will occur that will double the quantity PV. Put this all together and you have the ideal gas law. And the ideal gas law reads like this. It says pressure times volume. The pressure of the gas times the volume that gas occupies is the product of three things. The number of molecules, the amount of gas, in other words, a constant of nature, which I'll talk about, and the temperature. Let's look at that in more detail. P is the pressure. V is the volume. We're assuming this gas is in some kind of closed container, and that volume determines the volume of the gas. N is the number of molecules. K is called Boltzmann's constant. It's just a universal constant of nature, and it has an interesting unit. Its units are joules per Kelvin. It's a conversion, if you will, between temperature and energy, and we'll see more about why that's significant shortly. And it has the SI units, 1.38 times 10 to the minus 23 joules per Kelvin. And then finally, T is the temperature, and it's got to be in absolute units in the SI units. That means in the SI system, that means kelvins. It can't be in Fahrenheit. It can't be in Celsius. It could be in Rankine if you rewrote this in the right units, but it's almost universally used in the SI system, and then T is in kelvins. By the way, if you've had a chemistry course in particular, you may have seen the ideal gas law written PV equals nRT with a lowercase n. That lowercase n is the number of moles of the gas, a mole being 6 something times 10 to the 23 molecules, and R being a gas constant, which is analogous to Boltzmann's constant, but expressed in terms of moles. Chemists kind of prefer to write the ideal gas law as nRT on the right-hand side. We physicists tend to write it as nKT because that gets sort of more down to the basics, the number of individual molecules, the relationship between energy and temperature, and then the temperature. So I'm going to write the ideal gas law exclusively in this form, PV equals nKT, but if you've learned it as nRT, it's exactly the same thing. We just define the constant and the counting of molecules differently. So there's the ideal gas law, and I want to emphasize that that is an empirical law that was discovered by experiments on gases. And the main thrust of today's lecture is to understand where the ideal gas law comes from and understand how it must be true on the basis of simple Newtonian mechanics. So that's going to provide this wonderful link we're going to make between the microscopic interpretation, statistical mechanics, and the macroscopic interpretation, thermodynamics, with its large-scale quantities like temperature and pressure and volume. Now, I want to emphasize again, this law that you see here, there's no mention of what kind of gas it is. There's no number in there, no parameter that gets tweaked to make the difference between hydrogen and oxygen or nitrogen and radon or whatever the gas is. It's described if it's behaving ideally, which means if its molecules are really far apart, and a few other assumptions we'll get to shortly, then this law describes it without regard to what kind of gas it is. So let's move on, getting into the theory of the ideal gas. And I want to start with something I've mentioned I do to my students occasionally, and now I'm going to do it to you. We're going to have a math alert. This is really probably the first and maybe the biggest math alert in this course. There's a lot of math coming, more than usual, many screens on the big monitor. I'm going to go slowly, but we're going to have to slog through it. Why are we doing this math? Because it will lead to deep insights about physical reality. And that's the meaning of this math alert. Before we get into the math alert, I want to make some assumptions about the system I'm going to describe. I'm going to describe a system which is basically an ideal gas in some kind of closed container. So here are my assumptions. I assume there are identical molecules and each molecule has mass m. And you say, well, what about air? Well, air has oxygen, nitrogen, and a few other things. Well, we can generalize this to a gas with a mixture of molecules. But my assumption is we have identical molecules and each has mass m. There is no internal structure or size to these molecules. They aren't extended. They aren't carbon dioxide with 2 oxygens and 1 carbon, or water vapor, or H2 with 2 H's. That assumption we're going to relax by the end of this lecture. It turns out not to be essential to the idealness of the gas, but I'm going to start out with that assumption. Crucial assumption to the ideal gas. These molecules do not interact by any kind of long-range forces. There are no long-range interactions at a distance that these molecules undergo. They do not attract each other at a distance. They do not repel each other at a distance. If those assumptions are violated, then the gas does not behave ideally. And to some extent, all gases violate these assumptions slightly, but the violation is very small for gases whose molecules are far apart, which is why typical diffuse gases we deal with in everyday life, like the Earth's atmosphere under normal atmospheric conditions behave almost ideally. No long-range interaction forces. The only time the molecules interact is if they collide, and they collide like point-like billiard balls and go bouncing off, although I'm even going to assume there aren't any collisions. But that's not an essential assumption. It'll just make the math a little bit easier. And I'm going to assume, and this is generally true unless there's a really weird situation that sets up some preferred direction in a system, the molecules have a random distribution of velocities, and it's random in both direction and speed. Although the distribution of speeds, although it's random, has got a pattern to it, which we'll look at later. But a molecule is equally likely to be going this way or this way or this way. You say, wait a minute, isn't it more likely to be going down because of gravity? Well, gravity is so weak, and molecules are moving so fast at typical temperatures that that's not an issue. You know, you might imagine someplace like in the atmosphere of a neutron star with its enormous, immense gravity, where in fact there was a preferred direction of downward, and you'd have to work out a different theory. But for the ideal gas, in a situation like Earth's atmosphere with Earth's gravity, the distribution of speeds is random. There are other places where it's not random. For example, if you have an ionized gas which has its electrons separated from its protons, and you put it in what's called a magnetic field, we'll get to that in the next section of the course, it might have a preferred direction of its speeds. But I'm assuming, and this is true for ideal gases like the Earth's atmosphere, that there's a random distribution of velocities in direction. And here's another one right out of Newtonian mechanics, right out of the section on mechanics. The collisions with the container walls are elastic. And remember that an elastic collision is a collision that conserves kinetic energy. So when a molecule barrels into the wall of the container, it bounces back with the same energy it had going in. It doesn't give any of its energy to the wall. And of course, that's not perfectly true, but on average, it is quite well satisfied. So let's now move on and look, with our math alert in mind, at the ideal gas. So here we go with the theory of the ideal gas. What we're going to assume is we have a rectangular box containing a number of molecules. They're those identical molecules that are moving about with random speeds and random directions within the box. So I've indicated the molecules by little spheres. I've indicated their velocities by little arrows. They're moving about at random in that box. And there are n of them, capital N. That's how many molecules there are. And the end of the box here has a surface area A, and the box has a length L, and I'm going to call this the X direction, and then that's the Y direction, and that's the Z direction, but I'm really only going to care about the X direction because I'm going to generalize to the other two. So there's what we've got, a box of molecules. They're far apart, and they don't tend to interact. They collide with the walls of the container when they hit it, and they bounce off with the same energy they went in with, the ideal gas. Let's focus on just one molecule, which I will call molecule number I, the ith molecule. And I'll distinguish that molecule from all the others by using the subscript I. It has mass m. Our assumption was that all the molecules had the same mass, so the ith molecule has mass m. And it has an x component of its velocity, which is v sub x, the component of its velocity along the x direction. It may have a y component and a z component. I'm only concerned about the x component for now. And it's vxi because it's the x component of the ith molecule's velocity. The jth molecule or the 51st molecule or the 4,383rd molecule may have a different component of its velocity in the x direction. This is what the ith molecule has. The ith molecule collides with the right-hand end wall. Say it has, because it has an x component of its motion, so sooner or later it's going to hit the end of the container in the x direction. And when it does, it's going to exert a force. And here's a picture showing how that force comes about. So here comes the ith molecule in with some velocity. It's not entirely in the x direction, but it does have an x component. It's also got a y component. It hits the end wall at the maximum x value in this container, and it bounces off at the same angle it came in with. By the way, it has to do that to conserve momentum. So that's what it does, bounces off at the same angle it came in at. And notice that its y velocity, which was downward, its y component, is still downward. That hasn't been changed. Only the x component of the velocity has been changed. And that means the momentum of the particle has changed. How much has it changed? Well, if the particle simply came in and stuck to the wall, it would have lost all its momentum. And it would have gone from mvxi. Remember, momentum is the product of mass and velocity. It would have gone from mvx sub I to 0. It would have changed by mv sub x sub I. But no, that's not what happens. It bounces back. Its x component of motion reverses. It goes back out at the same velocity it came in with, the same x component of velocity, the same y component. The x component has changed direction, though, and that means it's not only given momentum to the wall, it's also gone back and gotten more momentum from the wall in that collision. And so the momentum change is delta p of the ith molecule, p standing for momentum, is twice what it had coming in. It would have been only 1 if the molecule had stopped, but when it comes bouncing back out again, it's gained momentum in the opposite direction. The total change has been twice what its initial momentum was. So delta pi is 2mvxi. That's the change in momentum for that molecule. And we know that when things change their momentum, forces are involved. The fundamental statement of Newton's second law, and here we're tying all this thermodynamic and gas stuff to fundamental Newtonian mechanics. Newton says force causes change in momentum. The fundamental statement of Newton is not F equals ma, but F equals rate of change of momentum. So there is a force exerted on the wall. You can think about it several ways. Clearly the momentum of the particle, the molecule, has changed. That means there's been a force on the molecule. Where did the force come from? The only place it could, from the wall. And by Newton's third law, if the wall exerted a force on the molecule exerts a force back on the wall. So we're really using Newtonian mechanics here. Now, let's ask how long after that collision with the wall the molecule returns. Now, I don't care what the molecule is doing, whether it's bouncing up and down like this or going straight back and forth in the x direction. As long as I know the x component of its velocity, that's what determines how long it takes to get from here back to there. And that's a distance L, and distance is speed times time, so the time involved is distance divided by speed, or L over Vx. And the question I want to ask is not how long does it take the molecule to get to the other end of the box, but how long after this collision does it take for the molecule to get back here? And that's twice L it's got to go. So that time is delta t is 2L over the speed Vx sub I. So it's going to return to the wall after that much time, and therefore the average force it exerts, the average force is going to be Fi, average with the bar for average, the change in momentum with respect to time, the rate of change of momentum on average. Now, that's not what really happens. What really happens is, bang, it has a collision, and there's a great big change in momentum briefly, and then there's nothing for a while, and it comes back, bang, again. But remember, there are zillions of molecules, and they're all bouncing off all the time, and we really only want to know what the average force is. And with so many of them, that will average out to a smooth, steady force. So that's the force from the ith molecule, and we can write that now as delta p, 2mvxi, divided by the time, delta t. And we can do a little algebra on that. That comes out, the v downstairs in the denominator becomes a v upstairs here. That's mv squared. And we got the L and the 2's cancel. Okay, first screen of the math alert. So there's our force, our average force due to the ith molecule bouncing back and forth, the average force on this surface area A. The average force on the wall due to all n molecules will be the sum of these forces over all the values of I. So I'm going to use the big Greek sigma that means sum, and the little I down there says sum over all the values of I. Molecule 1 plus molecule 2 plus blah, 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 blah. There it is. That's the average force on the wall due to all the molecules on that right-hand wall. Well, the mass of all the molecules is the same, so each term in that sum, it's like, A times, it's like AB plus AC. You can factor out the A, and it's A times B plus C. It's the same thing. I can factor out the M because it's the same for all molecules, and certainly the length of the box is the same. That doesn't depend on the molecules, so I can factor both those things out. So I've got M over L times this sum. Now the pressure is defined as the force per unit area, as we saw in the lectures on fluids, for example. So the pressure is the average force divided by the area, so I'll just take the average force and divide it by the area. There's the area, and then the area is multiplied by the length L, and that's the volume V of the box. It's area times its length. So this becomes the mass divided by the volume times this sum of all the x components. So now there's where we are. Another screen of math, but we're getting there. Multiply the right-hand side by 1. I can multiply anything by 1, doesn't change it, but I can multiply it by 1 in the form n over n, where n is the number of molecules. So I've got an n, and I'm going to put one n on the outside and one n on the inside of that sum. That's fine because n is a constant. It just multiplies through that sum. That quantity is the average, because it's a bunch of stuff added up and divided by the number of terms. It's the average of the squares of the x components, and I'm going to call it v sub x squared average. So I'm going to write this in a more simple form, nm v sub x squared average. So there's what we've got now. The pressure is the number of molecules, the mass divided by the volume by this average square velocity. The molecular motion is random. So the average of the x velocities and the y velocity squared and the z velocity squared has to be the same. Otherwise, we wouldn't have that random assumption satisfied. And if the x and y and z directions are all at right angles, which they are, then these velocities add by the Pythagorean theorem. So the average square of the entire velocity, the speed squared, is vx squared plus vy squared plus vz squared average. And consequently, v squared is 3vx squared, or 3vy squared average, or 3vz squared average, because they're all the same. Or equivalently, vx squared average is a third of the average total speed. And I'm going to take that result and put it in there. And then I get pressure is nm over 3v, v squared. Are you really feeling the math alert now? This is heavy, but we're almost there, and we're going to get a great big insight in the end. So there's where we are. The pressure is the number of molecules, the mass, divided by 3 times the velocity, times this average squared, just 3 times the volume, times this average squared velocity. Multiply by the volume, both sides. PV, that takes out the V down there, makes it PV on the left. Hey, this is beginning to look like the ideal gas law. Multiply the right side by 1 in the form 2 over 2. I got 2/3 n, I got a half mv average squared. Look at that. You know what that is. We dealt with that a lot in mechanics. That is the kinetic energy. In this case, that's the average kinetic energy. So there I am with PV equals 2/3 n times this term, which is the average kinetic energy. And let's now do a comparison with the ideal gas law. Both this theoretical result and the ideal gas law have PV on the left-hand side. What's on the rest on the right-hand side of the empirical law? It's KT, it's N, we got N on both of these, and we got KT. And so what we recognize here is that KT, the product of that Boltzmann constant with temperature, is 2/3 of the average kinetic energy. And there's that statement. And the huge insight we get from this is that temperature is a measure of the average molecular kinetic energy. That is the theory of the ideal gas. Temperature measures the average molecular kinetic energy, a very big, powerful result. Let me leave that result on the screen because it's so big and powerful, and let me do a quick demo that looks at that. So over here, I have a demonstration in which I've got a number of little ball bearings, and they're going to be agitated by what's actually a part of a loudspeaker, going to vibrate up and down rapidly. And I'm going to set those balls into motion. When they're moving relatively slowly, they still sort of form a solid layer at the bottom. That's essentially what a solid or liquid would be. But now as I increase the amplitude of that oscillation, you see the molecules beginning to bounce all around, and eventually they're bouncing around at random speeds and in random directions, and that is simulating a gas. And the bigger the amplitude of that motion, the faster those molecules are moving. And if I put this little thing in to represent, say, a piston that might be sticking in a cylinder of gas, you can see the pressure that system is exerting. You can see the volume increasing. And if I push down on this, I can feel the upward force increasing as I push down. That's a model for an ideal gas. We don't have 10 to the 23 molecules like we'd have in a gas, but we've got maybe 100 or 50 or something, and there's a simulation of what's going on in an ideal gas. Okay, well, let's just leave that on because that's such a powerful result, and let's just move on and look at a few other aspects of ideal gases, or maybe not such ideal gases. First of all, we found that the molecular speeds, the average is 3/2 kT. We can define a kind of average speed from that, which defines a so-called thermal speed, the average speed of a molecule under a given conditions. For example, at air, at room temperature, it's about 500 meters per second for the average speed of the molecules. There turns out to be a distribution of speeds called the Maxwell-Boltzmann distribution. There are pictures of it for 300 kelvins and 80 kelvins. And there is this mean thermal speed It's not quite the same as the peak, but it's pretty close. And then there's a high energy tail of faster molecules, and some molecules moving more slowly. So when I said there's a random distribution of molecular speeds, but it's got a pattern, this is the pattern of those molecular speeds. There's a theorem in thermodynamics, which I'm not going to prove, but it says this. It says if you have any system in thermodynamic equilibrium, the average molecular energy is a half of this quantity kT. And notice now, remember, K had the units of joules per Kelvin. So it's really a conversion between temperature and kinetic and molecular kinetic energy. And the rule is there's a half kT for every degree of freedom. What's a degree of freedom? It's a way a molecule can take on energy. And in the case of our ideal point particle molecules that were completely structureless, the only energy they have is the energy of their translational motion from place to place. And there are 3 degrees of freedom because there are 3 directions they can move in. So we conclude that the average kinetic energy, a half mv squared average, is 3/2 kT, which is exactly the result we got from our lengthy mathematical calculation. On the other hand, what if we have more complex molecules? What if we relax that assumption that the molecules are structureless? Well, if we have something that's monatomic like helium, it really is essentially a tiny little structureless point, and it has those 3 translational degrees of freedom. Go to something like oxygen or nitrogen. In addition to translation, those molecules can rotate about one of 2 different axes, and so they have 5 degrees of freedom, and that affects how they can take on energy. They get 5/2 kT of kinetic energy, of energy per molecule, and that affects their specific heats because it affects the amount of energy it takes to give them a certain change in their speeds. Go to diatomic and at high temperatures and they begin to undergo vibrations. That doesn't happen at low temperatures for certain quantum mechanical reasons. You get 3 translational degrees of freedom, 2 rotational, 1 vibrational kinetic energy, and 1 vibrational potential energy for a total of 7 degrees of freedom there. And finally, you look at triatomic molecules like water or nitrogen oxide, or they get very complicated. I didn't put carbon dioxide there because its molecules are in a straight line and it's a little less complicated. So complex molecules still behave as ideal gases, but their specific heats, the amount of energy it takes to raise the gas temperature, varies and depends on the structure of the molecule, on how many of these degrees of freedom the molecule can carry. The molecule can have the number of ways that energy can be divided in different modes of motion or potential energy in those molecules. And finally, let's move beyond the ideal gas to look at real gases and see how they're different. First of all, real molecules occupy space. There's molecule B coming toward molecule A, and that's the closest it can get because these molecules occupy space. And so there is a circle around molecule A whose diameter is twice that of molecule A, and that volume is excluded to molecule B. Its center, molecule B's center, can't get any closer than that distance from molecule A. And consequently, the volume V that enters our expressions should be actually a little bit less than the volume of the container. If the molecules are tiny and very far apart compared to their size, that excluded volume is so little we ignore it. But as you begin to cool a gas down and it gets close to the liquefaction point, then the molecules get close enough together that that effect comes in and makes a correction to the ideal gas law. Real molecules also exert forces on each other. They're weak forces, they're attractive, they drop off rapidly with distance. They have to do with something we'll talk about in the next section when we talk about electric forces and electric dipoles, and they actually have something to do with what's called the dipole moments of the molecules, and they involve very weak, very rapidly dwindling forces that are basically residues of electrical forces between molecules that, although they're neutral, have different distributions of electric charge. But the main point for our purposes here is there is associated a potential energy that means the temperature is no longer strictly a function of molecular kinetic energy, and that is the key to the ideal gas assumption. And so as a gas gets more dense and closer to liquefaction, then the assumptions of the ideal gas begin to break down. There is an approximate equation called the van der Waals equation that approximately describes gases if they don't get too close to liquefying, but ultimately they get so close we have to resort to the whole science of that phase diagram that I introduced in the previous lecture. So the ideal gas law is a beautiful approximation that applies to real gases in the real world to a very good extent, but as you begin to get near the place where you liquefy the gases, it breaks down first in minor ways, as I've described here, and then in more major ways. But most importantly, the ideal gas gives us this brilliant insight about temperature being a measure of molecular kinetic energy. Okay, let's wrap up. We've done here the kinetic theory of the ideal gas. We've been through a lot of heavy mathematics. It's confirmed the empirical observations that pressure times volume ought to be proportional to the number of molecules and the absolute temperature. It links the macroscopic physics, that is the subject of thermodynamics about heat and temperature, with the microscopic physics, statistical mechanics, Newtonian mechanics. We used things like elastic collisions. We used things like Newton's third law. We used a lot of stuff from mechanics to describe what was happening to these molecules, and we showed how the motions of the individual molecules gave us the ideal gas law. We got this brilliant insight that temperature is a measure of the average molecular kinetic energy. Half mv squared average is 3/2 kT for the simple structureless ideal gas. And then we elaborated looking at the molecular speed distribution, the thermal speed. We looked at more complex molecules. And we took a brief look at what happened when the ideal gas assumption breaks down as you go beyond that and toward liquefying a gas.